Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗚𝗟𝗟𝗟 and today we're gonna solve all 𝗙𝗢𝗪𝗓 2024 challenges. I mean the pawn ones, of course. So this CTF was beginner friendly. Every challenge was guided and pretty much self-explanatory. So let's start with the first one, onda, and we download the file here and unzip it with 𝗙𝗢𝗟𝗟𝗡 password. And what we see, we have 𝗙𝗘𝗥𝗘, okay, that's nice script over there, and readme.txt. Hello friends, this challenge is designed to help you get comfortable interacting with a remote instance while also guiding you through the installation of essential tools. If you encounter any issue or notice anything missing, feel free to reach out to me via DM 𝗪𝗚𝗟𝗟𝗪. To install the tools, run /𝗙𝗪𝗟𝗪𝗪 in your terminal. To interact with the challenge, spawn an instance and then use the command netcat_ip port. To run the solver script, run /solverpy _IP _port or blah blah blah. The HTTP fake flag for testing is not the flag, just a placeholder. After that, you simply send a string flag and get the flag. Okay, so we get exactly everything we need in order to play the challenge and solve it. So let's start to run the challenge locally. Enter new terminal /onda. So we have, let's go to cd challenge and we see the fake flag here and the onda file. So we run it and we see, hola mi amigos, send me the string flag and I will give you uno grande prize. So okay, we just send flag and we get the fake flag locally. Okay, so we try to the remote instance, we start an instance like this and netcat IP and port, and we get the same message with another color and we send the string flag and welcome to HTBOO Pawn Festival. So we got our first flag. The challenge was self-explanatory, guided and very easy for beginners. So let's proceed with the next one, which I think it was Mathematricks. So we unzip the file, hack the box, and another readme here. So let's go. Okay, my laptop is gonna explode. And we see connect to the IP and port given the answer to the questions to get the flag. Netcat is recommended. You can modify and use the solverpy script to send the payload or simply netcat. And the glibc folder is not needed, just for the challenge to run. Alright, again cd challenge and we see the fake flag here and we see a solver. That's pretty nice. It's like this. This is my template actually, and you need to modify the -1 value to the correct one. So we just have this. Nice. So let's just play the challenge. Okay, welcome to the mathematics contest. Rules: solve the math questions to get the flag. Some of them are tricky. Alright, play. Let the game begin. 1 + 1, 2. Amazing, nice. 2 - 1, 1. We have a mathematician among us. Yeah, that's me. Lit minus lit, 0. God of Math just entered the chat. Okay, I was hilarious there. And enter two numbers, 𝗪1 and 𝗪2, where 𝗪1 is positive and 𝗪2 is also positive, and 𝗪1 plus 𝗪2 are negative. Okay, if we take it realistically, this is not possible. I mean, if you enter two positive numbers, if you add them, you cannot possibly get, I mean, real numbers. Please, mathematicians, do not intrude the chat with, oh, we have imaginary numbers and stuff. No, for two integer numbers, this is not possible. So, what's the trick here? We're gonna open the challenge in a disassembler. I will go with Binary Ninja. And let's start with main. Okay, so here we have main. Let's change this to sudo C. And okay, while true, and this is our choice. Alright. Yeah, and we go to the game function. And here, okay, this one is the CANARY. It doesn't bother us in this case, just for me. And yeah, I check the answers here. 2, 1, and then blah blah blah. And we are here. Enter two numbers, 𝗪1, 𝗪2, where 𝗪1 is positive and 𝗪2 is positive. So let's say here we have 𝗪1, and right here we have 𝗪2, and we see this is an unsigned integer 64, unsigned integer 64, and here it checks if they are negative. Hacking School opens at late AM, don't miss it. So we cannot enter negative values for neither of them. And right here we see that it checks if it casts N2 and N1 to unsigned int 32, which is half of this. So can you find the bug here? After that, if we manage to do that, it will just red flag and print the flag to us. So what's the bug here actually? Let's take a look at this. In C, the int32 t max value is this one, and after that, if we add 1 to this, what do you think? Will it go to blah 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 48? We can test it with this test code here. So what we do, we initialize unsigned int 64t int max with this, the max value of the integer, and then we have, let's say, the number 1 with the same oh my god, I forgot the word, the same type, and then we print its value, and as hex here we see, same for x, that we don't even care here, and the result is, as the program declares, unsigned int 32 plus unsigned int 32. Our two numbers are cast to unsigned int 32, and let's print these values and see the results. So we GCC our program and run it, and let's see. So the int max has this value, which in hex is like this, 0x7ffffff. Okay, x is 1, and what we see, the result here is minus plus 1. So it is indeed 48, but it's all negative, because if you add 1 to this, it will become this, and it will trigger an integer overflow. So this way, let's take this here. This way we're gonna abuse the integer overflow and get the flag for the challenge. So Mathematricks 1, 2, 1, 0, and we take the max value and we add 9, and yeah, we got the flag here. And okay, let's play with the solver also. So here we change this to true to run it locally, and then you need to modify the -1. So this one was like 1, 2, 0 or 2, 1, 0, something like that. Then we have this, and then a random positive number like 9, or we can do 6, or we can do 69, whatever. I will keep that. And let's run it, Python solver, and yes, we got the flag with the automated solver with just some minor fixes. And let's also run this remotely. Here we go to Mathematricks, and we spawn an instance. We have to change this here to false, so it runs remotely. And then when the instance starts, let's refresh it, or wait. Okay, I'm just gonna refresh it. And my laptop is probably gonna land off. Yeah, we got the instance, and we do solver and this IP and port, and we should get the flag this way. Yeah, that's right. So this way we got the flag. And okay, we stop the instance, and let's proceed with the third challenge. I think it's what was it? El Teteo. Yeah, let's go. Oh, let's go with El Pipo first. So we unzip, hack the box, again, readme txt. In this challenge, you'll be provided with a binary file that runs on the server's backend. Your task is to reverse engineer the binary and identify the vulnerability. Do not attempt to connect via netcat. A web page is provided for interaction. Nice, okay. The input you submit is passed directly to the binary. If a few words don't get the job done, consider trying a bit more. Okay, this is a hint for a buffer overflow, probably. So let's go cd challenge, cat flag, dummy flag, and we run lpipo. Okay, not scary enough. And we got the flag, and also a segmentation fault. Okay, but why did this happen? Let's close this. And let's open it for lpipo, and we start the binary. We go to main, as always, here, sudo c, and what we see here, we have a buff initialized with 0x20, and we read 0x40 bytes to it. Okay, this is an obvious buffer overflow. And what does it say? var9. So let's say this is our target. target is initialized with 1. If target equals 1, not scary. So otherwise it calls read flag, which will print the flag to us. And what we're gonna do, we actually wanna overflow the buffer, fill the buffer with junk, and after that start overriding this. I'm gonna showcase it inside the debugger to be more clear. gdb Pipo. So be main run, and I'm gonna zoom out a bit, and here we see it initializes our buffer with 0x30, bam 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 bam, and then it moves 1 to RBP minus 1, and it moves RBP minus 0x30, which is the start of our buffer, to rax, and then rax is moved to RSI, which is the second argument of read, which is where we store our data. So as we can see, EDI is 0, so it reads from the keyboard, from stdin. The second argument is the buff, which starts here, and EDX is 0x40, which is how many bytes we're gonna read, we're gonna store to this buffer. So if we inspect this, what do we see? We see that, okay, we have our buffer. We can write here, 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 and here we see that there is a single 1, which is our target. And how many bytes can we write? We can write up to 0x40. And as we said, this one is 0x8, 0x10, so 8 bytes and another 8 bytes, 0x10 in total, 0x20 and 0x30. And we have even this addresses to override, but we don't care. So let's continue and see how it works. Let's say 1 2 3 4, 1 2 3 4, 1 2 3 4, and 1 2 3 4. We have written till here probably, so now we need another 4 for this. 1 2 3 4, and then we're gonna write 1 2 3 4 5 6 7 bytes. Let's do 7 bytes. 1 2 3 4 5, and a new line. So let's go with that. And damn. Okay. I miscounted. I'm a fucking idiot, but it's okay. But as we can see, this is arrays, our B's, C, D, E, and then A, B, C, D, E, and the new line. So we just needed to fill this address and another 8, and then another 8. So yeah, if we simply put a lot of A's, we're just gonna override it in the end and get the flag. And how does it work? Let's try and make it here as visual. So imagine the stack like okay, this is gonna be the worst representation of the stack, but it's okay. Oh my god, it's gonna be horrible. So imagine this as the stack, where here are the lower addresses and here are the higher addresses. So our buffer starts here, so we have, oh my god, so our buffer starts here, buff 0. I need to make a bigger stack. Okay, so our buffer starts here, and here we have another data, I mean the rest of the buffer. And above that, here we have, what was it, 0x20? If it was 0x20, I think it was 0x30. So here it's gonna be -1. So it's gonna be like that, which is, oh my god, I'm bad at maths. 16, 24. No. Okay, this is embarrassing. 48. So here's gonna be the 47th element of the buffer, and our target lies somewhere here. So imagine when you write your A's, you're gonna write A at the first element of the buffer, then a lot of A's until you reach the last element of the buffer. So we fill all these with A's, all these addresses here with A's, and after that, whatever we write next, it's gonna override this value. So this one has the value 1, and if we continue putting A's here, it's just gonna override this. Boom. And target will have the value A or whatever we put here, and it will pass the check. So that was, okay, this is ugly, but yeah, Picasso. And let's start the instance. What was it? El Pipo. Restart, and okay, the program said we do not netcut, we just go here, and nice. Okay, I did some good work here. And if we add a little A's, not scary, boo. But if we do many A's, boom, we get the flag. Here's the flag. You cannot see it because the resolution is bad, but yeah, here it is. This way we got the flag. We just simply overflow a buffer, overwrite the target's value, pass the check, and call read flag to print the flag for us. And on to the next one. I think it is 𝗙𝗘𝗥𝗘. So we have downloaded the file 𝗙𝗘𝗥𝗘, unzip it, pack the box, no readme this time, okay, cat flag, dummy flag. We still have a solver though. And what does it have? Okay, my template so far, and here we see shellcode from HTTP/shellstorm blah blah blah, and shellcode, add payload here, add the correct payload here, okay, and the rest of the solver is already done, so we only need to change this value here. But let's run the challenge first. 𝗙𝗘𝗥𝗘, ooh, glitchy, mi signo. I will do whatever you want, nice or naughty. Give me flag, please. And segmentation fault, something messed up. But why? First of all, let's run GDB here. And we see that the challenge has CANARY, an X unknown, enabled, and the stack is executable, and it has read, write, execute segments. That's very nice. An X unknown meaning an X is missing, so we can actually execute code on the stack. We can give it shellcode and the program will probably execute it. We can verify this again with the disassembler. So again, let's go to main, and we are here. So to see, and oh my god, all the banner is here. What have I done? But yes, okay. Right now we have a buffer. We initialized with 0x20 size, and we read 0x1f, so there is no buffer overflow here, but we can see that our buffer is actually executed. So whatever the buffer contains is executed in memory. So what are we gonna do? Thankfully the challenge gave us this link here, shellcode from HTTP/shellstorm. So we go to this page and we see that this guy has made an execute bin_sh 27 bytes payload, and here it explains the assembly, how it is, and that the program actually calls execv to spawn shell. And here is the payload in bytes in C, and he says the length of the payload is this many bytes, and it executes it, so it gets shell. So what is a shellcode? Actually are these bytes here, which are translated to this assembly, which is actually the lower level of an execv function, which is pretty much similar to system bin_sh. It actually spawns a shell. It gives us an interactive prompt, so we can interact with the program. So if we simply take this here and vim solver, so let's try first locally, and shellcode here, we're gonna remove that and insert that, and let's see Python solver, This should give us the flag locally, nice and clean. So the program actually stored into the buffer the shellcode we gave it, and it executed it. And it gave us shell, but why we didn't get shell and we get a flag? Because right here in my payload, instead of doing r.interactive to get shell, I actually send inside the shell the cat flag command, and I receive the line that contains the HTB string, which is the initials of the flag. So we skip the get shell part and get the flag instantly. And let's try this remotely. Just go here. And we start an instance. We refresh it. And we run the solver the same way as always, like this. And yep, we get the flag. So on to the last challenge, which is El Mundo. And we go back here. I have already downloaded the zip, hack the box. Again, no readme, just we already got a solver here again. Okay, the template, and change this n bytes 10, change this to the right amount, and read flag address 0x6969, not in me. Add the correct address, and the rest is already done for us. So let's run the challenge and see what it is. Oh, nice visuals. Oh, JOJO. So here we have exactly what I tried to draw previously, but it's nice and colorful. Yeah, it was nice these days. And as we can see, here is our buffer, the lower address, and then until here, boom, boom, boom. This is 32 bytes because our buffer is 32 bytes, and the last index is the 31 because we start from 0. And after that we have some local vars which take up to 2 addresses, as we can see, because each address is 8 bytes, and here we have 32, and then 40, 48, and then we have the RBP register, another 8 bytes, and then there is the return address. The return address is actually where the program intends to go in its correct flow. If we manage to override the return address, we can tell the program do not go where you should. I mean, for example, exit or print something. Go to the address I tell you, which might be a printf function, a read function, or the read flag function, which will open the flag for us. And this is actually our goal. And as we can see here, start of buffer, you write here from right to left. We see here the local variables and a dummy 0x the saved RBP and the saved return address. And the program says overflow the buffer, override the local variables with junk, override the saved RBP with junk, overwrite the return address with the address of read flag, and it also gives us the address. How generous. So let's play a bit, and let's say A, B, 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 and you need to add more than 9 bytes. Okay, thank you. And we actually see how it's represented in memory in real life, real time. This is the start of the buffer, and our first A's and our B's here in this address, and the new line here also. Let's try some more. A, B, 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 C, 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 D, 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 E, 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 E. And we see that we have written until here. Nice, but we still have some work to do. We also need to fill the whole address, this whole address, this whole address, this whole address, this whole address, and then overwrite this with the address of win. But why can we do that? If we go to GDB Mundo and we do 𝗙𝗥𝗥, we see that the challenge has no canary. So what is canary? And no pi. So let me briefly explain what these are. So, oh my god. So imagine here, you see that we have the RBP here, like this, and right here we have the return address. So the canary is a random value that is generated every time the program starts, and it's placed between RBP and the return address. So it's another 8 bytes that are between these two, between this and this. So if you try to override it before the program reaches the return address, it will check, is the canary the same that it was when the program started? If it is, okay, nothing happened, let's continue. Otherwise, the program will halt. It will not go to whatever the new return address is. If the canary is tampered, the program stops. So this is actually what the canary does. And what is pi? Pi is, if we see again Mundo, we see, for example, B main, disassembly. We see that main is 0x blah 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 40, 18, 57, and whatever. This is always constant. I mean, main, P main, P read flag, this will remain constant in every run. Okay, and this way we know where they are, we know their addresses, we can actually call them. So as long as I know the address of read flag, I can call it. If pi was enabled, we couldn't predict the actual address of the functions. I'm trying to remember if any of the previous challenges had probably Mathematricks. Hopefully. Check. Okay, so this challenge has pi. That will be a nice demonstration. As we can see already, we only get 4 bytes, 2 bytes of the address. And if we do disassembly, as we can see, everything is 0, 0, 0, 19, 24, blah blah blah. And you'll say, okay, this seems like a smaller address, and it seems constant to me. Yeah, these three are constant always, but all these will get randomized with each run. So if we run the program, as you can see, disass main, yeah, okay, these three were the same, but this one's changed to 55555. Because we are in the debugger right now, for simplicity, it will just showcase it with 55555. If we run it real time, this will get randomized every time. So we won't be able to actually call any function, read flag, main, or whatever. So this is what pi does. And let's go back to our challenge, 𝗪𝗪𝗪𝗪, and let's go again inside the debugger. And as we saw, check, no canary, no pi. We explained these protection mechanisms. So what we need to do now, what was the binary actually? Mundo. Oh yeah, overflow and override the return address with the address of read flag. So if we do it manually, it's actually 8 bytes. So 0x10, 0x20, 0x30, 38. So if theory is correct, with 0x38, and after that we will override the return address with whatever we want. So let's try our solver. So if we do here 0x38, and here we do the address of win. So this one is a bit, I'm gonna do it the dynamic way because it's simpler. So we're gonna do p64. p64 is a pawn tools function that actually packs the address. A bit of theory again. So imagine the address was like, it was this here. Fuck me again. So the address is this. As we said, every address should be 8 bytes, and this one is clearly not. We only see 3 bytes here. So you just need to add the rest of the bytes that are missing, which will be so this should be the, not this, this should be the correct address with all the correct bytes here. And what the p64 does, of course the binary cannot understand this. Okay, so we need to actually give it the bytes with little endian. What is little endian? So this is translated to, let me make it with a better value, 0x deadbeef is gonna be like backslash x ef backslash x b backslash x ad backslash x d. So you actually take the last byte ef and it becomes first, then you take another byte b and it goes second, and ad becomes third, and d becomes the last one. But the problem here is that still these are 4 bytes. The p64 does this and actually adds all the necessary zeros, so it will become like this. So this way the program will understand correctly what we're gonna send to it. So instead of doing this manually all the time, we will simply here we could simply put what we had as an address, the 0x40 something, or we can do E is here. It actually analyzed the binary and got all the addresses, the tables, the whatever, the functions. And from symbol table, we're gonna take the address of read flag. So this will automatically take the address of this function, pack it, and put it here. And okay, we don't need to pack it here because it is packed later in the payload. It is packed here. And let's see if everything is correct. We should not get anything. Now we should take the flag locally. Let's check. Nice. And that was the first 𝗙𝗚𝗟𝗟𝗡 challenge as the most difficult in this CTF. I hope I explained it. I didn't explain it so much in depth, but I hope you got the point. If you have any questions, you can leave a comment and I will answer, I will help you. So in order to get that remotely, we just change that to false. We go here, we open an instance. Let's refresh. And we do solver and the IP and port, and we got the flag. So these were the challenges for HTBOO 2024. They were made by me. I hope they were enjoyable and you learned something from them. If you have any comments, any feedback, any question, whatever, leave a comment. If you enjoyed the video, subscribe, and see you in the next one. Bye.